Okay, let's get started because I'm going to do this again on Tuesday during the tutorial. So because I want to get through this lecture, so I just want to give you a brief overview of what this course is about in case you were misinformed or think it's about something else. So this course, data visualization is sort of a topic. It's going to be learning about what is data visualization about as a sort of intellectual discipline, and also provide you with some tools for analyzing data. There's a narrative through this course that I'll follow, which is going to look a bit weird at the beginning. Data visualization is going to involve humans, so it's going to be a lot about how do humans perceive different things. There'll be a little bit of that, be some mathematics, some programming, etc. But I'm going to talk about that a lot more in the tutorial on Tuesday, okay? You already have an assignment to work on, which is kind of a goofy, kind of fun assignment. Every assignment will be worth different amounts of marks. All the administrative stuff I'll go over on Tuesday is available on the course website now. And what I'm going to do is I'm going to try to record these lectures. That doesn't mean you can rely on it, technology being what they are, so I still encourage you to attend the lectures. But if I can get them recorded and they're not bad quality, I'll post them on YouTube or something. So the narrative of the course, how I'm going to tie all of this material together is thinking about dimensionality. And we're going to begin with 0 dimensions, like just looking at a single number, one number. That's what today's lecture and Monday will be about. And then we'll move up to 1-dimensional data, 2-dimensional data, 2.5-dimensional data. So we'll kick around 2-dimensional plus for a bit, up to 3-dimensional data. There are a variety of things there. You can see 2-dimensional data. We'll talk about time series and maps and sort of those kinds of displays. And then we'll get up to 3-dimensional data. By stereo and perspective, you're doing a little bit of fusion of your vision stereo images in that assignment. Using the sort of thing in 3-dimensional data. And where I think things really get really interesting, but it's unfortunately towards the end of the course, trying to figure out how to deal with high-dimensional data, including up to tens, hundreds, maybe thousands of dimensions. So that's where we're going, and that's the narrative. Any questions on that? Okay, we'll talk about evaluation and everything else next day. Sorry, not next day, during the tutorial. So I think this is right. So we're going to begin with just talking about 0-dimensional data. That is a point, right? So it's just a single number in and of itself. And what does that mean? So to get you started, think about this. So the question is, what is that? Anybody know? It's a QR code, right? You've seen that sort of thing before. What's it tell you? Anybody recognize it? It's not telling you a whole heck of a lot, right? Oh, you recognize this? Okay, so the key here is this is an encoding of something, and we need some way of decoding this. So this is a QR code that originated with the Japanese automotive industry, and it's got a lot of information sort of in a 2-dimensional layout. But it's really hard for us to figure out what that is. So here's another code. Recognize this? So that's a barcode, right? So this is Universal Product Code. This is UPCA, the North American standard, a North American standard. And so it, again, encodes something and it needs to be decoded. The question is, what does it encode? Well, unlike the QR, I can give you some rules. So this is the thing I want you to decode. And the rules are, this is constructed in a very special way. So it's constructed to have a start digit, an end digit, a middle digit, and then a whole bunch of left digits, a whole bunch of right digits. And these are bit patterns that encode these numbers, these digits 0 through 9. So for example, a 0 is going to be 0, 0, 0, 1, 1, 1 if it appears on the left, and 110010 if it appears on the right. So you can tell which, with the start and the end, you can tell which is the beginning and the end of that digit, how to read it. Okay? So the digits here, that you get to use these digits on the left, those, and the last right digit is a check digit. So now you know the rules. This is a number. What's the number? So it's going to start with the start digits of 101, so that 1 is the first black line, then a 0, then a 1, and it proceeds thereon. All lines of that thickness. Okay, it's a little painful, right? You could do this. Might make a few mistakes. You have to look carefully where the digits begin and end. But it's hard. And it's hard for us to decode this thing. And it's because it wasn't made for us, right? It was made for a machine. So a machine is supposed to decode this thing, so it's set up to make that easy, just scanning a laser across that display. You know where the beginning, where the end is, and you can easily tell the width of the lines and decode that. You can have a machine do that fairly easily. But for a human, that's not so easy. So what I want you to think about, these are both visual representations of a number, the same number. Okay? And the number itself is encoded somehow in that visualization. So when we're thinking about data visualization, we're always going to have some picture, some form for the piece of data that we're looking at. And we want to be able to decode that. So this one is meant to be decoded by a machine, but not by humans. So what we really need are some things that are easy to decode by humans. And we're very different from machines. And principally, we're the product of a long, millions of years of evolution to get where we are here. So we're wired in a way that has benefited our evolution, not really for data analysis, but for other things. So we need an encoding that's designed to be decoded by a human. So here's one. Okay, this is specifically designed for humans, so that should be easy for us to decode. Okay? There it is. So what's the number? It's for humans. I understand you guys are all humans. Any idea? Sorry? 26. Okay, why? Okay, this is why I have you hand in assignments with R Markdown and LaTeX, because if you're writing 26 like that, we won't be able to recognize it. No, it's not 26, but that does look kind of like our numerals. So the question is this a better visualization than that or worse? And what would make it better? It's got to be something that we can instantly decode or quickly decode. So how about this? Here's another visualization of a number. Anybody have any idea what this is? Another human visualization. So this first one is Khmer. This is ancient Egyptian. Anybody want to guess what the number might be? 42. Why? So because there's 4 things here and 2 things there. Okay. Any other guesses? Yeah? 50. Because? Okay. That's a sophisticated interpretation, right? If they're base 12. 6. Why 6? So you don't care that these. Okay, these all encode the same number. 4 different ways of encoding that number. And This looked impossible. That one you guys struggled with even with the rules. That one, guessing it by matching it to the numerals you're used to. And that one, there were at least 3 guesses that we're interpreting this pattern in a sort of very human way. How many things are there? These are different from that, etc. So the question is, what number is this? Anybody want to vote? How many? So we have 42, 50, and 6. All those in favor of 42? All those in favor of 50? One diehard. Oh, 2. 6. Good man. Stand your ground. So if I gave you that cultural hint, you might know what it is. Those of you that are sci-fi. Right? That's the answer to the question of life, the universe, and everything, is 42. As everybody reads Hitchhiker's Guide to the Galaxy knows. So that's 42 in 4 different representations. And so if you think about this for a minute, you can think about what properties of a number might we encode. So a number, like what's in a number? What is it actually telling you about things? And what can you encode? So we're thinking about maybe we're going to have a visual representation, and that's a picture that encodes the number and which can be decoded, and has to be easily, efficiently, and accurately encoded and decoded. And you're usually decoding, it's visualization, you're decoding it by your eyeballs, right? You're just sort of looking at this through your visual system. And think about what can you encode? Well, it's got a unique identity that we want to be able to distinguish different numbers. This datum is different from that datum, so we want to be able to identify things visually. But it also may have something that related to quantity or extent or size, some sort of quantification. And numbers that we have can at least be partially ordered, right? You can say this is bigger than that, it's bigger than that, et cetera. That is, you can rank them from largest to smallest or smallest to largest. Or they may have a magnitude that actually makes sense, that it's actually a length measurement that has a magnitude. Okay, so it has has some meaning. And you want to be able to encode this depending on the situation, depending on the number, depending on the datum that you're encoding, it's going to have these different features. And you want to be able to encode the relevant features and not encode or not mislead the viewer with irrelevant features. So you want to think about how do these various encodings that we've looked at so far satisfy these properties. So you think about the barcode or the QR code, it certainly fails badly on this if we're doing the decoding. It does it really well if a machine's doing the decoding, right? But it's not so good for us. Certainly wins on this unique identity. Although as it becomes more complicated, for us it may be difficult to tell different QR codes apart. And you can encode a magnitude, the absolute magnitude of the value. So what we want to think about is, well, what numbers can be encoded and what's natural to us as human beings? So lots of people are doing work on this sort of thing that it's worth having a look at. All of these blue things are hyperlinked. You can go off and find the paper that I'm drawing this information from. But we found with animals, and we're a product of evolution, so we've got a lot of these traits in common with other animals. So many kinds of animals can distinguish numerosity, can distinguish number in some sense. Lots of things from pigeons to chimpanzees. And in particular, there's some work here on rhesus monkeys that have been shown that they can be trained to at least order numbers by magnitude from 1 to 9, even numbers that are new to them that they haven't been trained on, they can get that. And then naturally untrained, to select food sources that having a greater number, for example, they can distinguish 1 versus 2, 2 versus 3, 3 versus 4 and 5, but somehow not 3 versus 8, or 4 versus any of 5, 6, or 8. Like, it's kind of complicated what these animals can naturally do, rhesus monkeys. And also find that human infants can make similar kinds of distinctions as rhesus monkeys can in their early few months of life. So our ability depends upon a lot of things. It's innate. How are we made? What is this body? What is this brain? What is this visual system? How does it work? What is it? How does it recognize things? But also on culture. And so there are still the proverbial tribes that are somewhere in, unexplored areas. Amazon recently being interviewed and really only have words for one, two, many. They don't have words for a whole host of numbers, haven't needed them in their culture. They don't distinguish things. They perform poorly on numerical tasks for quantities beyond 3. It's unlikely they differ genetically very much from the rest of us. This is a cultural phenomenon. And they use their fingers beyond 3. So it's kind of what you encounter naturally. If they're only encountering small numbers, why would they worry about names for larger numbers? It just doesn't happen. It doesn't arise. It would be a waste of effort for them to have that kind of vocabulary. It'd be like us having strange names for every number, right? Rather than having a system. So here's ancient Egypt. It's not base 12. But you look at early number systems, and they're very, very natural, the visual representations. 1, 2, 3, 4, 5, arranged in a nice pattern so it's easy to recognize. And then you can think about this as the yoke for an ox, so go over the shoulders of a yoke. Imagine that there's a lot of those, tens of those, and this 100, finger 10,000. See lots of frogs, if you remember Old Testament kind of plagues of frogs and things, lots of frogs around the Nile. And this is which I call the WTF man. I mean, it's just so big, right? That's hard to imagine. And you see this in the hieroglyphics, and this is from a modern Egyptian building. But you can see, WTF, that's 1,000,000, 300,000, etc. 333, lots of these things. And that'll be a link to the building. So one of the greatest philosophers of the 20th century, Ludwig Wittgenstein, was interested about how early in his career, especially on how pictures provide meaning, sort of this picture theory of meaning. And so we want to think about, does the picture itself define what it represents? Is it really the definition? So when I say 4, right, I mean this, that's cuneiform wedge-shaped strokes inside of, it looks like 5 actually, inside clay, or it's Egyptian 4 rods, or Chinese 4 rods, Mayan or Attic Greek 4 things. It's very natural. So it's kind of, that's the definition. That's what we mean by 4, right? That's 4. Everybody universally agrees on it. And the early number systems show that there's no mistake. You can actually encode more complex numbers. So here's a strange number. This is an irrational number, right? The square root of 2. And we can find this in the dialogue, Meno's dialogue, which Plato wrote, describing Socrates' conversation with this slave boy and I guess the guy's owner that he was visiting. And he walks him through a series of things to find out that he actually knows the length of that. And the point is that this diagram embeds the definition of the square root of 2. If we sent this off to space, somebody may think they were trying to communicate the square root of 2. So the unit is this 1 square, right? So this whole thing has area 4, right? That means if we take half of each of the squares, each one of these pieces has area 1/2. This whole thing has area 2. So the length of that thing has to be square root of 2. We can actually physically see it even though it's mathematically irrational. It kind of embeds the meaning of the square root of 2. You can encode all kinds of things. I mean, Wittgenstein would have it, and I think if you've ever taught young children multiplication, this is kind of what we mean by multiplication. So 3 times 4, well, that's how many you get. It gives whole meaning, right, to the fact that you're squaring numbers, etc. That's why we say squaring or cubing in a higher dimension, right? So this picture itself is what we mean by multiplication. That's where it starts. Similarly, you have more complex things with just a series of pictures. So here's a proof of the theorem of Pythagoras without any abstract algebra of any sort, by just thinking about this triangle and the areas being preserved as we move triangles about. So this square, this white area, doesn't change its area in any of the pictures. All we have to do is slide things around, and we see that the square and the hypotenuse is the sum of the squares on the 2 sides. Simply, you could convince anybody in grade school that that would be the case from that sort of picture. So pictures are very, very powerful, used a lot in sort of demonstrating logic and definitions. So the other funny thing is that you are hardwired. It turns out that there actually are pieces of your brain that light up when you're exposed to numbers. And some pieces light up for particular numbers and other pieces for other numbers. And most of this action happens in this part of the brain. So your brain is divided up into lobes. Sort of frontal, that's kind of obvious. Occipital at the back, which is where most of the visual system is. If you've ever fallen off your bike and hit your head on the back, you see stars, that's why. Okay. And the parietal and temporal, you know, your temple. So researchers have found that a lot of the action happens inside this area here, the interparietal, I'll never pronounce these things right. So I won't just, the sulcus. It's probably sulcus. So this is where a lot of information about perception of numbers, but also your visual attention. A lot of this happens in here. And if we look at, we have a brain that's sort of wired for numbers. So a lot of the symbolic numerical processing occurs in that part of the brain. And as we saw with the cultures, nature and nurture both interact. So, but our brains are fairly plastic, so they adapt. The circuitry adapts to what it's exposed to. And so, because numbers are an essential part of our culture, we spend much time training ourselves, especially when young, about numbers. Like, it's a very important part of our culture to think about numbers and work with numbers. So we work with a lot more compared to those folks from the Amazon. And if you think about those Khmer numbers, if there was anybody here, you know, from Cambodia that could read Khmer, they would have instantly known what those were. We force those symbols on you when you're very young, the sort of the Hindu-Arabic numbers 0 to 9, so that you recognize them pretty immediately by the time you're, I don't know what, 6, 7 years old, the latest. Thing we know, these particular things light up, the part of our brain light up no matter how the number is presented, whether it's a number of dots or the word of that number or the symbol of that number, you're parsing it in the same part of your brain. And in our cultures at least, people tend to visualize, have a mental spatial representation of numbers from left to right, going from small to large. That seems to be the case. That's probably because that's the way we've been training ourselves to go from in that direction. When numbers get very large and very small, we tend to not be able to tell the differences between them. And so there's sort of this logarithmic compression. So in math, we learn about natural numbers. And these are the counting numbers, maybe with 0 added or not. But as humans, these are not our natural numbers, mainly because of those dot, dot, dots. And that where we have difficulty with very large numbers and very small numbers. And it's important to realize that in trying to convey information about the size of numbers to anybody that's viewing a visualization. So our modern world, unfortunately, deals with very, very, very large numbers and very, very, very small numbers. Very, very large numbers in the size of the debt in the country, or how much waste is being produced, et cetera. Very small numbers, the probability of winning the lottery or some risk event. We're very bad at understanding those numbers because we're not wired for them, right? Once they get too large, they're all the same size. Once they get too small, they're all small. So I want you to think about that for a minute. Think about, imagine, get a visual representation for the number. And if I ask you to think of the number 3, you're probably going to think of 3 things. You're going to visualize 3 dots, etc. If I ask you about the number 5, you're going to visualize 5 things, 5 dots probably. And if you're used to gaming, right, 5 in that, probably even in that pattern. Right, that's a very easy way to recognize all 5. If I ask you to think about 7, okay, you can probably do that. You can do that in a variety of ways. I mean, look at 2 sides of two faces of a die, put them together, whatever's familiar. 12, okay, 2 6s, 20, it's getting a little harder. 50 is getting a little harder. Maybe I have to do 5 by 10 things. And think about what if they got a lot bigger? Like these numbers are still puny and they start to get difficult to imagine. So for example, the number 9 million. Like, can you imagine how big 9 million is? It's pretty hard. Well, that's actually a visual representation of 9 million. And to get some sense of the size of 9 million, you have a question? Yeah, that's right. I mean, if you think about, if you think about debt, the national debt, once it gets beyond a certain point, you just have no concept of actually how large that is, right? I mean, if it's $1 billion or $2 billion, I don't know what that is. It's just so completely outside of my ordinary experience. And unfortunately, we have to communicate that kind of information. And again, particularly for small risk things like 1 in 10 million, 1 in 20 million chance of getting something happening to you, how do you measure that? Should you be that concerned about it? Should it affect your life in any way? So you want to be able to convey that information. So this is 9 million, and we're going to zoom in on this X. So that's the X. And you see it's pixelated. There's a little more information there, a little more on the part of it, the center here. Can you see what these things are? So these are all children's blocks. 9 million children's blocks. And it's an important number. This before the Obamacare, Affordable Health Act, same thing. These are the number of American children that had no health coverage in 2007. No health coverage. Just to get some sense of the magnitude of that problem. And for reference, there's somebody standing beside all of the blocks lined up. So that gives you some sense of what 9 million are. And if you imagine every one of those little blocks being a kid without health care, now there's a narrative. Now there's a story. Now there's something you can kind of attach meaning to. Right? So you get a better sense of this 9 million, and it's an important number. It's important for us to understand numbers like that because they are things that we have to make decisions about as a society. So there are lots of such numbers, and this guy that produced this is an artist named Chris Jordan. And I'll just go at another one of these. So this is, what is this? 20,500 tuna. And this is an important number. It's the average number of tuna fished from the world's ocean in minutes. You say, well, how big is that? Well, as before, this whole thing is constructed with everything in here is a fish. There are 20,500 tunas. give you some sense of the magnitude of 20,500. And it's clearly, again, an important social problem to think about. So we have to have some understanding of this. And there are lots more. I encourage you to visit his site. So big numbers are really hard. The other thing that's hard are small numbers. And you think about how would you visualize a fractional? How would you visualize a ratio? So here, for example, 1/3, that's sort of a natural way to get three things, mark one of them. And you might do that as three separate things, three blocks contiguous, or maybe just a bar. And this one's a little harder because I'm not really sure that's at 1/3. I know that one's at 1/3. I have a sense that this one is, but this one's a little harder because I'm looking more at the length of that bar. I don't have these clues. The 6th is the same sort of way. Again, the 6th, is that a 6th, is that a 7th? I don't know, but it's a lot easier to tell that it's a 6th than either of these two. So think about these other guys, and then these are sort of visual fractions. It's a very good way to present just a small fraction graphically. So communicating risk. So people communicate risks as a visual fraction. This gives people a much better sense of, say, the probability of a death or probability of getting a disease, et cetera. If you tell them 3 out of 100, they may have difficulty appreciating what that is. But you put up 100 icons of people, and you color 3 of them, they've got a much better immediate sense of what 3/100ths is. Okay? So you're trying to communicate that information. Here's 15 out of 1,000 people. So you've got 1,000 icons, et cetera. And again, this is a link to go look and play with various visual fractions. So what if the fractions get a lot smaller? And they come up, so a single pixel on a 17-inch monitor with this resolution. This is its length in meters, 34 over 100,000. The average diameter of a human hair, meters, 1/10,000th of a meter, wavelength of light, et cetera. And here's one that comes up every day. You can talk to anybody in your family or friends that have bought lottery tickets. The probability of winning a Lotto 649, the grand prize. 1 in roughly 14 million. How small is that? So I would venture to say that once that number is small enough, once it gets below 1 in 10,000 or something, people don't distinguish even smaller numbers. So you'd like to convey this information. That's an interesting link as well. So here's an example. A few years ago, a student and I put together some posters, Rachel Dean, the probability of winning Lotto 649. So one thing you might imagine is that all of the railway tracks between Windsor and Quebec City, right through down to Niagara Falls, think of that railway track and think about a baseball, the size of a baseball, and then place that baseball somewhere along that track. And now you pay me money to guess exactly where. So that sort of thing, it gives so to this story, again, a narrative and an understandable length measure. You could also turn it into a different kind of story by changing the scale. So I've inverted this from looking at the probability of winning, which is very low, to the expected time it takes for your first win of the large prize, or the main prize. Okay? So there's a timeline here. It was 2008 when we did this, and we look back at when you had to start buying tickets and how many per week in order to won the grand prize by 2008. Okay? So if we blow this up a bit, so if I was playing Keno, and I was actually buying 100 tickets every week, I should have started about 413 years ago, right? Roughly when Shakespeare wrote Romeo and Juliet. If I'm playing Lotto 649 and 114 tickets I buy every week, it's 2,359 years ago, which is roughly 2000, it's going to be here, roughly when Alexander the Great. So should have started buying tickets then, and maybe you'd be expected to win by 2008. And if you're just buying one a week, well, there's some evidence that Homo sapiens had diverged, but your Neanderthal ancestor should have been buying one ticket a week every week for Lotto 649 to expect to win by 2008, or by now. So this kind of timeline, inverting it into something else, again with a narrative, you give people a chance of understanding their actual chance of winning. Another thing is to turn this into expectation. So I bet so much and they pay out on average. So average, what do you lose on average? Then you can run various lotteries by how much money you pay and how much you expect to win. And that removes the randomness in the sense that it all becomes expectation. Same as that timeline, expected time to win. So for Lotto 64.9, they pay out $1.10 on every $2 bet. So they're making money. Here's another way of thinking about risk. There's something called a micromort. And what a micromort is, if you're the chance of death being 1 in a million, okay? So 1 in a million chances of death. So if your probability of death is 1 in a million, that's called a micromort. And you think about, well, how many micromorts, because you're going through risk every day, how many micromorts are you spending just going about your daily business? And looking at the statistics that are around, like looking at England and Wales out of 54 million people who died from external causes, accidents, murders, suicides, etc. Roughly daily living is about a micromort a day. That's the risk you're running. Which means now I can think about other activities. Hang gliding, riding a motorcycle, walking, running, driving a car, and think about how many micromorts of risk. And it turns out they're much less risk than you might think. If I recall correctly, and I probably don't, but the hang gliding is on the order of about 6 micromorts. So you know 6 times your daily risk. Well, maybe that doesn't make it sound quite as risky, right? You're willing to expend that risk. I mean, that's like 6 days worth of risk just in one shot. You're spending. So this notion of a micromort sort of brings home the risk in a way that's maybe understandable. How many days of life am I risking in this one activity? So, good, I've got some of these. Risk of dying from anesthetic is about, so that's not the surgery, just the anesthetic, is about 10 micromorts. Question? So there's a couple things you might be suggesting. One is that knowing that it's only 6, that I will behave in a more risky fashion as a result of that knowledge. That could be the case. The other thing is that your natural behavior may be very different from mine anyway, so that your micromort risk is different from mine. These are, like any statistics, these are got to be averaged over a whole group of people. So that's looking at all hang gliding events that they've got information on and the number of deaths. So what they determine what the chances of death is. So as soon as you start conditioning on other things, like that you're different from me, of course the numbers have to change because you're looking at conditional distributions. Okay? So, but for the population, these a lot of UK numbers, so just dying from anesthetic is about 10 micromorts. Just going to a hospital and getting anesthetic. That seems to be the risk. So, instead you might look at how many micromorts you spend on each activity, or for example, if I want to travel from here to Toronto, what's the cheapest way to travel? how many micromorts am I spending if I compared to riding a motorcycle, compared to, right? I'm going to be at different risk levels, and that's why cars will often be safer traveling. Another way to try to, and this one's a little more complicated, and I encourage you to look at the web page here. Is thinking about microlives. We all have an expected lifetime. Other circumstances, but let's just say conditional sex. So the notion is that a micro life is about 30 minutes of that expected lifetime. So let's call that 30 minutes expected lifetime. And you can ask yourself, well, what would it cost me to engage in such and so an activity? The guy that does these things, David Spiegelhalter, does a nice little video. I mean, he likes a lager in the evening, and he likes bacon sandwiches, right? So we know those are bad for you, particularly if you have 2 or more lagers. They're bad for you, but how bad? So maybe I like bacon sandwiches so much that I'm willing to spend, so many micro lives on doing it. It's worth it for me. So it's sort of trying to ground that number, ground that risk. And again, these are averages over the whole time. You're not going to lose and expect a half hour of your life if you smoke 2 cigarettes today. But it's sort of the effect of average time. So I'm going to wrap up here with these, just a summary here. The very large numbers and very small numbers are hard for us to get our heads around. They don't come up that led to our natural selection. So we find that very hard to get our heads around. They're often outside of cultures, period. So in some sense, those are unnatural. So very large, very small numbers, I want you to think that those are really not natural numbers, no matter what we've told you before. In a math class they will be, but not in a data visualization class. They're just not natural. And so when you're trying to convey that, especially as statisticians, as data analysts, you're trying to convey that to the public, to somebody else, you have to realize that you are much more embedded with small and large numbers than a typical person, and you're not as well embedded as you think you are. Okay? And as soon as I start introducing probability and uncertainty, this gets even more difficult to convey. Right? Okay, that's all I wanted to say today.